Welcome to the second module of this course on Fourier Series. To build a solid understanding of the fundamentals of the Fourier Series in a clear and approachable manner, this module begins with a brief recap of key concepts from elementary mathematics. These foundational concepts are essential for grasping the principles behind the Fourier Series. Let us begin our discussion with vectors and orthogonality. Most physical quantities can be broadly classified into two types: scalars and vectors. A scalar is a physical quantity that has magnitude only and no direction. Mathematically, scalars are represented solely by their magnitude. For example, the quantity time has a defined magnitude represented as t and is the same in all the directions, indicating that it has no specific direction. Common examples of scalars include time, temperature, pressure, and energy. On the other hand, a vector is a physical quantity that has both magnitude and direction. Mathematically, vectors are expressed using their magnitude and the direction in which they act. The direction of a vector can be along x, y, or z axis. For instance, the quantity force has both a magnitude and a specific direction, say along the x axis. This is similar to how Earth's gravitational force always acts towards its center. Mathematically, a force of magnitude Fx acting along a direction of x-axis is represented as Fx I hat or Fx I caret, where I hat or I caret is the unit vector in the x direction. Here, Fx denotes the magnitude of the force and I hat indicates the direction. If the force has components along all the three axes, x, y, and z, with each component having a defined magnitude, the vector form of the force is Fx I hat plus Fy j hat plus Fz k hat. Please note that some engineers use x hat, y hat, and z hat to indicate directions, which is essentially the same as I hat, j hat, and k hat. The total magnitude of the force in this case is F total is equal to square root Fx square plus Fy square plus Fz square as shown here. Other examples of vectors include velocity, acceleration, displacement, and electric field. Let us now discuss a fundamental operation between two vectors, the dot product. Consider two general vectors A and B expressed in terms of their components along the x, y, and z axis as shown here. The dot product is an operation defined between two vectors and is represented with a small dot between them as A dot B. Formally, the dot product of vectors A and B is defined as the transpose of the vector A multiplied by the vector B, which finally simplifies to ax bx plus ay by plus az bz. Without going into the geometrical interpretations or vector projections, two vectors A and B are said to be orthogonal or perpendicular if their dot product equals 0. Mathematically, this condition is written as A dot B is equal to 0, which serves as a quick check for orthogonality between vectors. For example, the dot product of the two vectors considered here is 0, demonstrating that they are orthogonal or perpendicular to each other. Understanding orthogonality in vectors will later help us grasp how different sine and cosine functions interact in the Fourier domain. The quiz section at the end of this module includes various examples to help reinforce this concept. I strongly encourage you to work through these questions carefully. In this video, we briefly introduced the concept of vectors and orthogonality. The next video will extend these ideas to the concept of orthogonal functions. I hope you found this video helpful. Thanks for watching and see you in the next video.